Hi everybody, today we're starting chapter 5, 5.1, where we are approximating the area under the curve. So this is the introduction to this idea of integration, which integration means exactly that, area under a curve, versus when we did the derivative, that was finding the slope to the tangent line. Okay? So we're using rectangles in order to approximate today. So a real-world connection here, connection with distance, velocity, and time. So distance traveled can be found exactly, right? If we have this velocity graph up top, and it's saying that we are traveling at 5 meters per second for 2 seconds. Well, that means that we traveled 10 meters. And if we are traveling at 15 meters per second for 1 second, there's another 15, and so forth. So if we added up the areas of those rectangles, it would tell us exactly how far we traveled. But that's where, if the velocity was like choppy, like can we jump from 5 to 15 meters per second? We can't. It has to be a smooth curve. So the picture at the bottom is actually more realistic of what we would have, our velocity curve, and then an approximation of the area that we are traveling, right? So in this case, we have an under approximation. There's some empty space there that we're not accounting for. Okay, so there's 3 ways to approximate the area under the curve using rectangles. We have right endpoint approximation, where the height of the rectangle is obtained using the right endpoint. So this moment right here is where we would take the y coordinate, which is the height of the graph, and we would have the delta x, which is the base of the rectangle. And if we multiply those two together, that would give us the area of a singular rectangle. And you can see in this approximation, all of our rectangles are created using the right corner as the height. Then there's left endpoint approximation. So similar, but now the left corner is where we would use for the height of each rectangle. And then there's midpoint, right? Midpoint tends to be the most accurate. It kind of counteracts that under and over approximation. Okay, so pause this video, make sure you take notes here. This is important. Here's our steps. So we're going to divide the intervals into n equal pieces, each with width b minus a divided by n. So the interval will be given, we'll be told how many rectangles to create, and then using that information we create the width of each rectangle, or the delta x. Then we'll calculate the height of each rectangle using the endpoints. So based on the x coordinates we get that we break up using our delta x, we then evaluate the function at those x points, and that would give us the height. We multiply height times base, and we find the sum of that to estimate the area under the curve. So conceptually, it's not so bad, right? We're finding areas of rectangles and we're adding them up. The values aren't always going to be that easy to work with. All right, so this example says calculate R4 and R6 for f of x equals x squared on the interval from 1 to 3. So we'll take a look at both for this example, okay? We're going to do R4 first. So R4, that notation is saying find the right hand approximation using 4 rectangles. So always start with dividing the interval into n equal pieces. Our interval is given as 1 to 3. So delta x is equal to 3 minus 1 divided by 4, which is going to be 1/2. Okay? So we already have a nice graph shown. You know, this isn't always given. I do recommend getting a quick sketch so you have an understanding of what you're looking for. The curve is the x squared. The rectangles are given. And if we know that we're starting from 1 until 3, and we are using a delta x of 1/2, the next important step is to figure out, well, what are the x coordinates that split up our interval, right? And if the delta x is 1/2 and the right corner needs to be touching, the first x value is the most important one. And if we're doing right approximation, the first x value will always be your a from your interval plus a delta x. That will give you the right-hand side of that first rectangle. So in this case, we have 1 plus 1/2, which is 3/2. And then each consecutive, or each of the next rectangles, will be adding 1/2. So our x values are really 3/2, 4 halves, 5 halves, 6 halves, until we have 4 of them. Also, when we're using right endpoint approximation, the right side of the interval will always be used. So once you have your x coordinates, you're basically taking those and making a table of values. You need the corresponding y values. Right? So we obtain those by taking 3 halves, 4 halves, 5 halves, 6 halves, and plugging them into the f of x equaling x squared. Right? So if I take 3 halves and I square it, I get 9/4. And if I take 2 or 4 halves and I square it, I get 4. If I take 5 halves, I get 25/4. And then 3 squared is 9. So those are the x values and the y values. The y values, again, are the heights of the rectangles. Okay, the base of all of those rectangles are delta x. So you could individually find each rectangle, or you could say, if I know that if I know that the width is a half, then I can sum my heights together using the distributive property here. And this would be much easier to put in your calculator or do mental pencil and paper if you had to. So we end up with 1/2. I went to fourths here because that way I could add my fractions more easily. And I end up with 43/4, which is my right approximation using 4 rectangles. Okay. So now let's do the same exact problem real quick doing R6. Okay. So with R6, our delta x does change. You can see the picture of the graph is a little bit different. The rectangles are skinnier. There are more of them. So now we do 3 minus 1 divided by 6 equals 2/6 or 1/3. Our x1, which is always the most important, is 1 plus 1/3, which is 4/3. And then from there, I can list all of my x's, so 4/3, 5/3, 6/3, 7/3, 8/3, and 9/3. So I end at 3, and I also have 6 of them. My corresponding y coordinates, if I square them, I'm just going to put it in the parentheses here. So if I square 4/3, I have 16/9. Then I have 25/9, 36/9, 49/9, 64/9, and 81/9. Adding all those up and multiplying by 1/3, you would end with 271/27 as your R6. So the big question for this section, and as we move through this chapter, is how do we get as close as possible to the actual area under the curve? What's going to help us minimize over or under approximation? Okay. So keep that in mind as we move through these problems. This question is asking for R6 on x to the -1. I'm going to skip this. We can go through more examples in class, but I want to move on to L6 instead. Okay, so we're going to do L6 for x to the -1 from 2 to 4. Okay. So again, you can get a quick sketch if you would like. X to the -1, or 1 over x, roughly looks like that. We're going from 2 until 4, so it's just that little slice in between, and we're breaking it up into 6 rectangles. And this time, we want left endpoint approximation, so I'm only going to draw 1 rectangle there so I don't get it too messy. But the left endpoint matters, which means when I'm coming up with my x1, right, my first x value that I'm going to use is my a value. So that's the main difference between R and L, is how you begin your list of x's. Okay. All right, so back to step 1, coming up with my delta x is 4 minus 2 divided by 6, which is 1/3. Okay. So my x1 starts with a value this time, which is, in this case, 2. So my list of x's would be 6/3, 7/3, 8/3, 9/3, 10/3, and 11/3. This time I don't end with my b value, I end one less than my b value. So I have 1, 2, 3, 4, 5, 6 x's. I would need the corresponding y's, which would be the heights. So the y's, the corresponding y's, I just make a quick table like this. My function, that's where they always come from, is x to the negative 1. So if I take 6/3 and I evaluate it by adding a -1 exponent, it's going to flip it. So my y's just become the reciprocals for all of these. Okay. My L6 is then going to be equal to delta x times the sum of the heights. 3/6, 3/7, 3/9. Definitely go to your calculator here. You don't need to get a common denominator when all of the denominators are different. So it's approximately equal to 0.737, which it's a very small sliver here, right? The rational function approaches your x-axis, so it's not surprising that it's really, really small. Okay. The next thing that I'm going to put up here is notation that only AP kids need to look at. Okay, so regular class, don't worry about this notation. I'm going to put it up here, but I'll definitely talk about it more in class. And the notation is using summation. So I would write this summation. L6 is 1/3 0 to 6, or I'm sorry, 0 to 5. 3/6 plus j. And it equals the same exact thing. Not a huge topic on the AP exam, but it's been brought up, so I wanted to make sure that it's something you see. Again, we'll talk about it more in depth in class. So here are the two formulas that we were just using, where you have your delta x plus those y values or function values for all of the heights, the sum of them. Notice my right, like I was saying, the first x value is a plus delta x, but my left, the first x value is just the a. So now we're going to move into midpoint approximation. Okay. So M6 for x to the -1 from 2 to 4. So same exact function, okay? Same exact delta x, same exact graphical picture, except for the middle of our rectangles are now touching. So this is the region that we're looking at. Now if I were to sketch a rectangle in here, just one, this is what I'm looking at. Okay. So halfway across my rectangle is where the height would be used, which would be half of a delta x. Okay. So my delta x is 1/3, or maybe it's helpful to keep it as 2/6. My x values, they're not going to start at a, they're not going to start at a plus delta x, they're going to start at a plus half a delta x. That's where the first x value begins. So in this case, I have 2, or 6, or 12/6, I should say. and I'm going to add 1/6 to it. So I have 13/6 is my first x value. But after that, to get to my next my next height, I am going a full delta x because I'm going from the middle of the first rectangle to the middle of the second rectangle. So now I'm going to add, my list of x's are 13/6. I'm going to add 2/6, so I have 15/6, 17/6, 19/6, 21/6, and 23/6. So your x values for midpoint approximation should always be symmetrical between your interval, a to b. So on each side, I'm a 1/6 away from my a or my b. So m6 is equal to, or approximately equal to, 1/3 delta x times the sum of the heights. Remember that these are my x values. I need my y values. So my y values are going to come by reciprocating these fractions because of the function x to the -1. So 6/13 plus 6/15 plus 6/17, 6/19, 6/21, 6/23. And that is approximately equal to 0.692. So again, for the summation notation, we're going to f of a plus j minus 1/2 now because it's midpoint, delta x, which is f of 2 plus j minus 1/2 times 1/3, which ends up being 1/2 plus j over 3 minus 1/6, 6 over 12 plus 2j minus 1. So m6 equals 1/3 So again, this is for AP, AB, and BC only. Regular students do not have to look at this. Simply put, you just need to understand that this also means the area. So you might look at a multiple choice question and you'll be looking at something like this, and you need to extract and understand that they're saying take the limit as n approaches infinity. Again, this is something we will go through in class. Similarly, also for AP, this is more notation. The power sums, you may or may not see that, so we'll go through it more. Okay, and now for everybody. Find the area under the graph of y equals f of x equaling x from 0 to 4 in 3 ways. Way 1 is geometry, so that's just the only way I want to focus right now. If the question's saying use geometry, well, let's just try not to overthink this. Let's graph f of x equaling x. It's just a line going through the origin slope 1. From 0 to 4 is here to here. Geometrically, what shape did we just find? We found a triangle. So in this case, I wouldn't want to use rectangle approximation because I can geometrically find the exact area of this triangle, right? F of x equaling x, or y equaling x. If my x coordinate is 4, then my y coordinate, my height is also 4. So I can calculate this exactly with 1/2 base height, getting 8. Okay. Okay, this is the last example I want to end this lesson with. The other examples that are in here, this one we'll take a look at in AP class, as well as example 3. And the final example is something that we can do in all classes, and we can take a look at RL and M6 for this one.